executables. I'm very excited to no longer have to talk about keys. Today we get to talk about executables. These are the things that affect the world around them. They utilize keys, produce keys, interact with the environment, all sorts of fun stuff. They are the stuff you think about when you think about AI. If keys and locks are cause, then executables are the effects. So let's begin. KLEP was originally called KLAP, Key Lock Action Process. It was intended that actions would do their things, release a key, this would validate other actions, and so on. This chain of influences is known as the process in KLEP. While we still have the process, I found that only using actions and only actions was too limiting. So I abstracted that approach to 4 base executables: sensors, which produce keys from the world around it; actions, which affect the world around it based on keys; routers, which modify keys into other keys; and goals, which manage a series of executables. Sensors, actions, routers, and goals. With their powers combined, they make SARG. SARG is the shorthand mnemonic system that I have developed to help me make KLEP processes. The method is very simple: key to lock to executable to key. That's it. In the next video, I will show you examples of sensors, actions, and routers while using SARG. Goals will be its own video, as goals are unfortunately complex. As they manage the series of executables, goals are also executables. So you can have a goal that manages a series of goals, and you can see where the complexity can creep in. All of these are built with the KLEP executable base class. The executable base class serves as a foundation for all executables. Being an abstract method, it provides essential functionality and structure while being modular, allowing you to override its specific base implementations to put in your own logic. It also requires specific behaviors to be implemented in derived classes so that all critical functions are present and ready to be used by the system. This is present in the onComplete function, and currently that is the only function that is necessitated by my code. The irony is that we use a process and not a plan. So in almost every executable I use, I have it return a dummy value of true. And this is because of goals, and we'll get to that eventually. But for now, as you can see, the critical and necessitated method that my abstract class demands you put in is not all that critical. That is the way of life. This is because we use a process, and with a process, completion is more of a fuzzy concept than in a direct plan, where completion demands that you move on to the next step. Let's take a look at the virtual methods present. These methods provide default implementations that can be overridden in derived classes for tailored behavior. So what does that mean? That means that you can keep them the way they are and they will work, or you can override them with your own logic, and that will fire if anything is calling that function. Or you can combine it with method.base, and that will call the method's base code and then your addition. The virtual methods include init for initialization logic specific to that executable, executable updates, which acts as a hub for updates, ensuring controlled execution flow. Execute defines what the executable does when it runs. Can validate and can execute checks if the executable has the necessary conditions met via locks to begin or continue execution. Cleanup handles all necessary cleanup after an executable is done, such as releasing resources or resetting states. Our big two that you'll use all the time is executable updates and execute. This is where the actual work gets done. If you want a character to pick up an item when you left click on that object, then that logic is going to reside in one of these functions depending on your approach. As stated above, executable updates is the update method of the executable. That's a weird sentence, meaning that you can think of it in the same way as you would your main loop with whatever code structure you utilize. In the case of Unity, you can think of it as the update function. These are fired prior to the selection process, which we'll touch upon briefly in a bit, and all executables that are part of the neuron will fire their executable updates. This is important to understand because if you have an executable that is a child of an object, it's not firing its executable updates until it gets picked up by a KLEP agent. Then that knowledge gets added to that agent's knowledge base, and the executable update will begin firing, unlike a normal update, which will operate all the time. These are fired irregardless of validation, unlike execute, which needs both validation and the ability to execute to fire. This means that you can have an action that has an executable update cycle, and then if valid, it can also fire its execute method. Validity and the ability to execute are checked in our is valid and can execute methods. These may be overridden to use custom checks. I do not do that, but you can, and that's an important part of KLEP. It allows you to do whatever you want. So let's take a deeper look at these functions. If we look at the check for validation, it starts by assuming that it's valid. This is important because if we have no locks assigned to the validation field, then it's open and therefore should be considered valid. Think of these as like doors. If the door has no locks, you're free to go inside and do the things. If we have locks assigned, we check each of those locks and the conditions of those locks. If you review the video covering locks, you can see that it holds a method to check if it's satisfied. So we call that with the list of the current keys that were released from the buffer. If it's not satisfied, we break out of the loop and we return false. If we can validate it, we grab all of those keys that validated it and mark them as is in use. And once again, this flag is used only for debug reasons currently. However, obviously, you can do so much more with that. Then we return our original guess that it was valid. Our can execute is the exact same structure, so we don't need to cover that. Yay! So instead, I will ask a deeper question. Why do we have a two-step validation process? The two-step validation process in KLEP, consisting of can validate and can execute, is designed to differentiate between the possibility of an action and its appropriateness or soundness. I forget which one is which, but currently we check if a executable is valid and then we check if it is possible. Maybe that should be flipped around, but that check isn't so hard to modify. The important part is that this distinction exists and can be critical in complex systems, be them game orientated or be them in a different field, where not every executable action that is possible is necessarily desirable or makes sense in the current context. So, an example, firing a gun. Imagine a scenario in a video game where an AI agent has a gun and it can be fired and reloaded. Here's how the two-step validation process might look like. First, we check if we can actually do the thing. This check determines if the gun is in a state where it can physically be given an action like reloading. For example, it checks keys for, is there ammo available to reload it? Is the magazine not already full? Here, can validate returns true if the gun has a free capacity in the magazine and there is some spare ammunition to load it. Then we check if it makes sense or is advisable to perform this action. For example, we might consider keys like, is the agent under fire? Is the agent in a safe place? In these cases, can execute might return false if the agent is under heavy fire and exposed, where reloading could be risky and potentially lethal because it's going to take time. However, it would return true if the agent is in a safe position, making it a tactically sound decision at that moment to reload. Can execute checks for technical feasibility. It ensures that all technical and mechanical prerequisites for an action are met. It is purely objective check unrelated to the system's strategic or tactical context. Can validate checks for contextual appropriateness, evaluating whether the action makes sense in the current scenario, considering broader dynamics, player strategy, potential consequences, as well as preventing missteps and preventing actions that, while possible, might be detrimental or suboptimal given the current circumstances in your scenario. Both of these are used by the agent in firing off their executables. And just as we have two flavors of condition checks, we have two flavors of executables. We either have those that are in tandem or those that are not. In tandem executables may fire alongside any other executable as long as it is both valid and it can execute. Those that are marked as not in tandem, only one may fire out of the entire bunch for that frame. Therefore, you can fire as many layers of the in-tandem executables as you want for a frame, but you can only fire one non-in-tandem. Well, this then comes down to the actual I part of AI. How do you evaluate if one executable is better than another? This comes into play with our calculate attraction method. This function calculates a numerical value representing the attractiveness of an executable based on keys and locks. If you review my key and lock videos, you'll see that all keys and all locks have an attraction value. This attractiveness is a conceptual abstraction of how well that key matches the conditions required to validate and execute the action. You can make it more nuanced if you want by having it evaluate exactly how well that key and lock combination fits. But for my system, which is a simple system, as I am a simple man, does not need more complexity and a more nuanced analytic. So we start by checking validity and executability to make sure that we're only going to return attraction scores of a valid and executable, which is a weird thing to say there. This is redundant and will change in the near future for optimization and stuff like that. But for now, in my implementation, we iterate through all locks for both can validate and can execute. We then collect those attraction scores of the lock and the prettiest key or keys of any key that satisfied the conditions of that lock. Remember, think of conditions as the pin of a lock and the data of our keys as the teeth of that key. So that is what is unlocking that lock. Then, once we have that actions total, we can do the same for all the other actions. We aggregate those, select the ones with the highest attraction, and this is both for is valid and can execute to ensure that the feasibility and desirability of initiating the actions are evaluated. This combined total is what we use as our metric to decide what to select. If you want, you could very well return both individually and utilize that with some other logic in your system to increase the selection process. However, as I said before, I am a simple man with simple needs, so I don't do that in my implementation. So an example is if we have executable 1 and executable 2, and both are satisfied by key 1. Key 1's attraction is tied to an int called ammo, so the more ammo it has, the prettier the key is. By setting up different attractions on your locks, you guarantee one is more likely to be selected. By setting up negative attractions to locks, you deprioritize that attraction. And just as we can change the attraction of a key, say tying it to our integer called ammo, we can also tie an attraction of a lock to something, such as like the inverse distance, so closer means bigger number, of an enemy. And we can see how that might dynamically influence which actions are critical and important and should be selected for that frame. It leads to a contextual aware selection. Just like in GOAP, goal-oriented action planning, where actions are prioritized based on their cost and contribution towards achieving a goal, in my system, executables are selected based on the calculated attractiveness. This ensures that the most appropriate actions are taken, balancing between resources available and the situation's demands. By using this, the dynamic nature of changing key and lock attraction based on game states, we allow for responsive and adaptive AI behavior, which can plan without planning. In other words, following a process of actions that are not only possible but also optimal under the current contextual conditions. This cascade of influences, this cause and effect, allows for a more nimble solution to evolve over a rigid do this then do that structure of planning. We will in later videos talk about how KLEP deals with situations where that ordered approach is needed, but it can do that as well if it needs to do it. It just prefers to play things by ear. This means that if we are affecting locks in such a way where we are changing data, and as locks are scriptable objects, then we will want to have a deep copy of our locks for our executables, so that any changes that we make to them do not affect the rest of the system. This is done in our awake function, which is fired first thing upon being born into the game space, or any other system you are developing for. This copies the locks, allowing us to change their attraction at runtime and even change the conditions that they need. Initialization happens in our init function, which is called by the neuron when it is adding an executable to its knowledge pool. Init is a virtual function that can be overridden to allow for custom logic and setup. This is called each time it's incorporated by the neuron, by any neuron. So this means if you need to set up a transform or return a rigid body, then this happens prior to the execution each and every time that's incorporated to any other neuron. This allows you to have things like hot swappable user controls, for example, that are drag and drop and just work out of the box for any of your agents as long as they're set up in the same way. And you can override AI controls on the drop of a hat. You can also utilize the same executables across development cycles for different projects and products. KLEP is that modular. So we have a register event function that is also called by the neuron for registering with /bridge and the UES, the Universal Event System. This allows us to override it and add in custom events that this will listen for and then fire the corresponding logic. Just as we have an init that gets called when incorporating the exe into the neuron's knowledges, we have a cleanup and unregister function that does as the name suggests. Both are called when a knowledge is removed from a neuron. This allows you to pull out a knowledge from the system and the system will not break because of it. So if you want to turn off player controls, you can just delete that knowledge and then it's gone. Finally, we have push to buffer and push to neuron. Both are controlled by a convenient bool at the top. This lets you decide if you want speed and to have the keys it issues considered in frame, or the data purity by allowing it to be pushed to the buffer and have everything else considered. Or you can do both. We pass it the KCD, key creation data, and a string that we can use for whatever. Usually it's for debug. Then this raises an event with the UES and passes it those fields where the key manager, which is covered in my last video, is listening for those events. It then creates a key and pushes it to the buffer or the neuron or both as directed by the bools. Now I really don't want to overwhelm you, and I would love to continue this explanation. However, I don't have the energy to edit an hour-long video, and I feel that this has been the important parts of KLEP executable base for the script. The next video will look into explicit implementations of a sensor, of a router, and of an action. And we'll be able to see it pushing keys to the system, using keys and locks, all that fun stuff. And honestly, we've already kind of seen a lot of that, but this is practical use case scenarios. If you need to reach out to me, do so at Twitter. Otherwise, I got an email that I don't check, and I got a Ko-Fi that isn't set up. So it is what it is. If you want to play with the code, it's on GitHub. But to be honest, I've fixed a lot of bugs since putting it on there, and so it's very out of date. I feel as if I'm doing one of those old school medieval copyright protection that they used to do back in the day, where they would just their plans would be drawn incorrectly, and so if you were to try to copy their plans without their without their consent, then you wouldn't know that their plans were drawn incorrectly. So maybe it's a little bit like that, or maybe it's just me being foolish and very lazy. Either way, I thank you so much for your time, and thank you so much for your interest.